Greetings and welcome to our presentation entitled Prescribed Time Stabilization of Controllable Arbitrary Order Systems using Switch State Feedback. My name is Ramon, and this work is co-authored with Dr. Julie Orlo from CSS and Dr. Luis Aguilar from CITEDI IPM. The outline of this presentation is divided in 5 items, as I'm showing here. Let us start with the motivation behind this work. We are motivated by applications with critical convergence time, like the working of a Viper robot and the missile interception task. Both of them require that the control goal is achieved in a small time window. In order to deal with that kind of applications requiring a certain time function that is bounded, in the literature we can find finite, fixed, and prescribed time stabilization. In the first case, in finite time stabilization, we have a differential equation that its solutions are steered to the origin, like I'm showing here on the right, in a time that is upper bounded by the right-hand side of this inequality. In this case, this upper bound depends on the initial conditions, as I'm showing here. There are other kinds of stabilization called fixed time stabilization. In this case, trajectories steered to the origin in a time that is upper bounded by a constant, regardless of initial conditions. In this case, for instance, this upper bound is pi. Doesn't matter where it starts, it's always comes to the origin in time no longer than pi. But as you can see here, this upper bound is not a priori set. That's why another kind of fixed time stabilization called recently prescribed time stabilization in the work of Song and et al. This work, for instance, this differential equation, its solution goes to the origin in a time no longer than this capital T that I'm showing here. And that's called prescribed time. In this work, we will be developing a controller that works with prescribed time stabilization. In our problem statement, we will be considering a system in the normal form Wang, where capital lambda and b are given here, and eta is a state vector. Eta super 0 is the initial state vector. T sub 0 is the initial instant, U is a control input, and W collects uncertainties, disturbances. We will assume in the sequel that the state vector eta is available for feedback, and also that the external disturbance W is smooth and uniformly bounded by a purely known constant capital N. So the problem is to ensure that trajectories of our system are steered to 0 for all time greater than T sub 0 plus capital T, independent of the initial state eta super 0, with capital T, a positive number, arbitrarily small and selected a priori, and of course regardless of whichever admissible disturbance W affects the system. To solve the aforementioned control problem, we propose a hybrid controller. This state feedback hybrid control algorithm is given in two. It's composed of two elements. First one is acting if the norm of the state vector is different from 0, and the second one is acting otherwise. This control algorithm given in 2, P is a square matrix, A transpose is a vector, nu depending on all states is an autonomous state feedback. The time varying matrix M depends on the time varying gain mu1 given in 5, and is inherited from the previous work from John Song et al. In 2017. The ingredients of the autonomous substructure is the HOSM-based control algorithm 6, which is capable of stabilizing the system 7 in finite time with the controller gains given in A, under a certain choice of positive constant mu sub I, independent of K1. Thus, the class loop 6-7 possesses a finite time equilibrium point at the origin eta equals 0, regardless of admissible disturbances W. This was proven in the corollary 7 in the work from Zavala and Moreno. The ingredients of the non-autonomous substructure are the time-scale transformation S, its derivative with respect to T, which yield mu1, the time varying gain, and its inverse T depending on S. Here in the left, we have a figure showing a plot of T depending on S, where S is going from 0 to infinity, and T depending on S is going from 0 to the prescribed time capital T only. The design in S time starts from the controllable system in bidiagonal form 1 where the matrices A and P are given here. In this matrix A is composed of the matrix capital lambda and a diagonal matrix defined by this delta sub I, which are real values. The C1 is the controllability matrix of the pair A and P. The second step is to transform to a system in controllable canonical form using the change of coordinates 2, which yields 3, where this math called A is given, as we can see in the right. For this new system, C2 its controllability matrix, and P, the matrix used in the change of coordinates, results from the both controllability matrices. The third step is to design the controller for the system in controllable canonical form 3, which yields the controller 4, where new is the state feedback from Zavala and Moreno, and A transpose is a vector containing the coefficients of the characteristic polynomial already mentioned. So the last step is to design the controller for the system in bidiagonal form. We start from the already obtained controller for the system in controllable canonical form 4 and use the inverse of the change of coordinates to get controller for the bidiagonal canonical form 1, which is given in 6. Now, to go from S time to T time, we start from the S time controller for the system in bidiagonal form 6 and define the matrix A with the components in the mean diagonal delta sub I in this way. And also, we pre-specify the perturbation in this form, which of course satisfies that it's also upper bounded by capital N. Next, we apply the time scale and state transformation given in 7 and 8 with the time varying matrix M depending on time given here and the time varying gain mu1 given here. And we get the hybrid state feedback control algorithm 10 for the perturbed arbitrary order chain of integrators 9. The main result of this presentation is summarized in this theorem. Consider system 9 and its controller 10 specified with appropriate parameters and an arbitrarily small capital T independent of initial conditions and unvisible disturbances. Then the closed loop dynamics 9/10 escape to the origin eta equals 0 in fixed time with the convergence time capital T sub 0 lower than capital T and with the bounded time varying gain mu1 applied at the initial stage between 0 capital T sub 0 only, where T sub 0 is defined in 11. Now we would like to illustrate the capabilities of the hybrid controller in an illustrative example where we compare prescribed time and fixed time controller from the literature with our proposal. First place, the plant is given after third order chain of integrators affected by disturbance W upper bounded by 0.5. The hybrid controller is given here with its components given down. The controller parameters are given in this part of the presentation where the prescribed time was set to 2 seconds. The prescribed time controller from theorem 3 in Zond et al. It's brought here to comparison purposes. The controller is given in this way with the parameters and the time varying mu1 also it's involved here. Parameters are set as we are showing this the bottom of the slide with the prescribed time in this case set to 2.25 to avoid numerical issues as mentioned by the authors of this controller. We also brought from the literature a fixed time controller from theorem 5 in Lopez Ramirez et al. The controller structure is given here and is accompanied with the parameters beta dependent on this value of the argument W and with the parameters that we are showing here in the bottom of this slide. We use this following simulation setup. Initial conditions are set to 1 in all the 3 states. Euler forward integration method was used with the sampling time as we are showing here. In the first comparison, we compare with the prescribed time controller from Zond et al. Its acronym is given by PT. Our proposal is defined as PTFG, prescribed time with finite gains control algorithm. In this slide, we show the
the states eta 1, eta 2, and we can see how our controller, we can see how trajectories are steered to the origin in our case, while in the case with the prescribed time controller, trajectories converge only to a neighborhood of the origin. In this slide we show the third state. It's the same case happens here. The same happens here, where the state are steered only to a neighborhood of the origin in the case of a prescribed time algorithm, and in our case the state are steered to the origin regardless of the disturbance affecting the system. In both cases, the control input remains bounded, as shown in the right, in the figure in the right. Comparison with the fixed time control algorithm from Lopez et al. Is given in this slide. The states eta 1 and eta 2 are shown here. As we can see here, our proposal is one more time, robust against disturbances, while the algorithm from Lopez et al. It's only robust in the sense of practical input state stability. This is also viewed in this figure where we are showing the state eta. Both control input, of course, remains bounded.
At the end of this presentation, we would like to give some conclusions. First, a switched controller capable of prescribed time stabilization in the presence of uniformly bounded external disturbances is proposed for an arbitrary order perturbed chain of integrators. While the linear time-varying feedback controller component is not viable beyond the convergence time, whereas the HOSM component is finite time stabilizing only, rather than prescribed time stabilizing, the proposed synthesis does not suffer from such drawbacks, ensuring both the viability of the closed-loop system over the infinite horizon and its prescribed time stability. Theoretical results are illustrated in a numerical simulation study with a third-order perturbed system in normal form. Extension of the present development to prescribed time output feedback stabilization of nonlinear systems, which are now necessarily presented in normal form, is a non-challenging problem calling for further investigations. Thank you very much for your attention. We left in the bottom the contact information in case of any further discussion.